Welcome everyone to another seminar at Physics Latam. Today's speaker does not need an introduction, but I will do it anyway. We have the honor of having with us Professor Robert Myers. He's a global leader in theoretical physics, and he's currently the director of Perimeter Institute. He's a pioneer of the study of black holes motivated by string theory. Myers' landmark contributions include the discovery of the Meyer-Perry metric, advanced black hole entropy, and the Myers effect. A new relationship between quantum entanglement and space-time geometry. Myers received his PhD from Princeton in '86, and he held a postdoctoral position at the Calif Institute and served as a faculty at McGill University before joining Perimeter Institute in Waterloo in 2001. He is worldwide recognized for his significant contribution and holography. If you have any question during the seminar, please do not hesitate to ask. And now I leave you with Rod. Please go ahead.
Okay, thank you very much. It's a pleasure to be here today and to give this lecture. I have this title, Scanning New Horizons, Information, Gravity, and Holography. What I'm really going to be talking about is sort of an area of science or string theory that, goes by the rubric or under the umbrella called It from Qubit. Now, in fact, I'm wearing an It from Qubit. I guess you can't quite see the It from Qubit t-shirt from our very first conference. It was originally intended as the name of a certain collaboration, but it sort of extended and sort of has become the moniker of a particular set of ideas. And as it's described there, it's a collision of new ideas. And in particular, on one side of the collision, we have gravity, and on the other side, we have information theory. And in fact, to make the collision even more interesting, I'm going to add quantum to both of those. So we have quantum gravity, quantum information theory. And if you ask what is the engine that's really driving this collision, it's holography. That's the topic of your course, of course. Now, I've described it as a collision. Other folks might describe it as a confluence of new ideas or a nexus of new ideas, a dialogue. But I really like collision because it's a good physics term. We collide things in experiments, and as the picture indicates, a collision is an event with a lot of energy. Things go flying in all directions, and we're not really quite sure where things are going to land. And I think that's an appropriate description of the area that I'm going to be talking about. Even though we've been working on this field for, almost a decade now, there are really a lot of new exciting ideas coming through every year, and new directions are opening up. And so I hope I convey some of that to you in today's lecture. But I'm going to start with, the right-hand side of our collision. And so there we have quantum gravity. And so, I'm not going to give you a lecture on quantum gravity. I'm going to give you a couple of slides to give you a perspective. Basically, we have two marvelous theories. We've got Einstein's theory of gravity, general relativity. And the amazing thing that Einstein realized is that gravity, which we thought of as a force, is actually a manifestation of an interesting theory of space-time geometry. Now, this has been the source of all sorts of new ideas, the ideas of black holes, gravitational waves, an expanding universe. But it's also a theory that's faced numerous, very precise tests, experimental tests to confirm the theory. The most exciting new tests of general relativity, of course, are the discovery of gravitational waves in 2016, or the observation, not the discovery, the observation of gravitational waves in earthbound experiments. And the other was the observation of a black hole by the Event Horizon Telescope in 2019. And so what are we doing? We're combining that with quantum theory. That's, again, an amazing theory. It's a rich source of new ideas and innovation. And it's also a theory that's really, survived or been scrutinized with extremely precise experimental tests. So what could be so hard in combining these two marvelous theories? Well, it's really that, quantum theory is a theory where, things are not precise and instead fluctuate. And so in a quantum theory of gravity, what is it that's going to fluctuate? Well, it's the space-time geometry itself. When examined at very, very short distance scales, we're going to see all sorts of, or we imagine that we'll see all sorts of crazy fluctuation. And the question then is, well, how do we make sense of space-time itself? Or how do we make sense of physics in this context or in this regime? And of course, there are different ideas. Some people here at the Perimeter Institute are working on modifying the idea of geometry at very short distances. My own area is string theory. And so what we're really doing is we're introducing many new degrees of freedom when we examine physics at very short distance scales. Today, what we're doing, or what I'm going to be talking about, is bringing in new tools, new techniques from the area of quantum information theory to give us a new perspective and new insights into this very old and very challenging problem. Now, one of the new insights that we've had in the past 25 years or so is holography, namely the ADS-CFT correspondence. And you all know what that is, but a simple description is that this is really a dictionary. We've got one set of physical phenomena, but we've got two languages with which we can describe those phenomena. On one side here, I've got quantum gravity with a negative cosmological constant. And on the other side, I have a quantum field theory without any intrinsic scales. Namely, here we have a conformal field theory. And the simplest solution on this side, of course, is anti-de Sitter space. And hence, that's the ADS and the CFT of the ADS-CFT. Now, one of the remarkable things is that this theory, the gravity theory, lives in what I'll call d+1 dimensions, or what we call the bulk space-time, whereas the conformal field theory only lives in d dimensions, or the boundary space-time. And so this is a really radical reformulation to go from a theory of gravity in one number of dimensions to a theory without gravity in one lower dimension. But it's something that's really been scrutinized by theorists over the past 25 years, and it survived literally, hundreds, if not thousands, of tests to really understand this correspondence or this dictionary. And of course, I've introduced the word holography here because we're relating two different theories in different space-time dimensions. And so the next slide is this familiar slide. And what that is it's telling you that we're going to make a shift or I'm going to make a shift in my discussion. And it's reminding me that I should pause and ask if there are any questions. I know that was a very quick introduction, and maybe we don't have questions yet, but I'll pause and I'll ask anyway. Are there any questions at this point?
I have a quick question. You say
sure.
modifying the spectrum. What do you mean by a spectrum exactly?
Well, if we look at the excitations of the theory, we have lots of new degrees of freedom, namely most of the time we focus our attention on the lowest energy or the massless degrees of freedom in string theory. And those are the graviton, the photons, the various other kinds of form fields, the corresponding superpartners, and we write down effective actions like supergravity actions. But in fact, the full theory contains extra degrees of freedom, namely the excited states of the string, which are very, very massive, and they have masses that are of the order of the Planck scale. And so that's what I mean when I start looking at the theory at very short distances. I'm going to see that my particles aren't just particles, they're actually strings. Does that convey the idea?
Okay.
Okay.
Yeah, I thought you mean modifying the spectrum of the string theory, actually.
Okay. No. It's just that we see that there's a much bigger spectrum than just a theory of general relativity or general relativity coupled to some massless fields.
Okay, thank you. Is there any other question?
In any event, then I've sort of given a super quick introduction to these ideas, and now we're going to move towards quantum information. And here, really, the key idea is quantum entanglement. And what is that all about? It's really a very simple idea. When in a quantum theory, I have several subsystems or I have different degrees of freedom, I still describe all of those degrees of freedom with a single wave function. And so the different subsystems or the different degrees of freedom can have unforeseen or correlations that I would not see in a classical world. And so we call it quantum entanglement. Of course, this was first pointed out or discovered by Einstein, Podolsky, and Rosen. They wrote a paper in which they illustrated this. Einstein and his friends called it spooky action at a distance. And they actually, wrote that paper trying to illustrate what they thought was an inconsistency or a paradox that, just didn't make sense. And so to illustrate that in their mind, quantum theory was an incomplete theory or it needed more. But in fact, now we really think of entanglement as the key difference between a quantum theory or a quantum world and a classical theory or a classical world. And so, there is the field of quantum information where this entanglement now becomes a resource for ultra-fast communication or ultra-fast computations or ultra-secure communications. Quantum information or the ideas of entanglement have also been making great headroads in condensed matter theory, where it's really now understood to be the key to various exotic phases of matter or new phenomena. And I listed a few here, like quantum Hall fluids or quantum Hall states, high TC or unconventional superconductors, and something known as quantum spin liquids, new magnetic states of matter. Now, what I'm going to try and illustrate in the discussion today, or what you'll get actually just a glimpse of, is that ideas regarding entanglement also are playing an important role, or playing a role at least, in quantum field theory and quantum gravity and the way that we understand them now. So I've written a simple wave function here for two polarizations in this EPR experiment where Alice and Bob are making observations, which could be light years apart, but it's always true when they collect their data and come together, they realize that every time that Alice measured a spin up or a vertically polarized photon, Bob measured a horizontally polarized photon or vice versa. Now, we might compare that to other wave functions that, here's some other simple wave functions incorporating these two spins or two polarizations. They're more complicated. They now have 4 components rather than just 2. And we can ask, are these states entangled? And, if you fool around with this first wave or that first state long enough, you'll realize that it separates into 2 separate components, a component or a wave function for the first spin and a wave function for the second spin. And so in this way, the 2 spins aren't really talking about to each other. They really are governed by separate factors in the overall state. And so that's a state with no entanglement. On the other hand, in this second wave function or the second state where all I did is flip that sign, you can try as hard as you will, but you can never divide it up or factorize the state in this way. And so that's an indication that this state is entangled. Now, that's an easy enough exercise if I have two spins. But what if I want to have a system like a quantum many-body system in condensed matter physics where there are, hundreds or thousands or 10 to the, very large number of spins all together in a lattice? How are we going to describe entanglement or determine whether the states are entangled or not? Well, what we would like is a relatively simple diagnostic that gives us a numerical coefficient or measure of whether or not there is entanglement and the degree of entanglement. And so this is where our quantum information friends introduce the idea of entanglement entropy. And the idea is I have this big system with many degrees of freedom. I divide it into two. So now I have A and the rest of the system called B. I trace out the degrees of freedom in B, and I'm left with a mixed state or a density matrix that's describing the degrees of freedom in A. And then I just apply von Neumann's formula for entropy. I take trace rho log rho, I add a minus sign, and that entropy is what we call the entanglement entropy. So in our two examples, or our three examples rather, I can try and apply that formula and say I trace out the left or the second polarization. I'll get a density matrix that looks like this. And when I apply that formula, I find that there's an entanglement entropy of log 2, which indicates that the two spins or the two polarizations were entangled. In this particular case, if I go through the same exercise, I will find that the entanglement entropy is 0. And finally, if I apply it to this last state, I again find that there's a log 2 for the entanglement entropy. So in fact, there's what we say, 1 unit of entanglement between the degrees of freedom in these two wave functions. Now, in fact, there are some bonus slides. I'm assuming that my slides will get posted somewhere, and there's some bonus slides of other examples, other ways to illustrate or to think about entanglement entropy. But I'm going to move to some general comments about quantum field theory, because that's really going to be an arena where we're interested in measuring entanglement. And we're going to use entanglement entropy to do the job. Again, we're told that we should divide the system into two subsystems. And so typically what we do is, if this is a constant time slice, we'll divide that time slice into two regions, the inside and the outside, or A and B. We're going to trace out the degrees of freedom in the outside region, and that leaves us with a density matrix describing the degrees of freedom in the inside or the A region. And then we are instructed to apply this formula. Now, this is an extremely challenging calculation, even in the case of a free field theory, say just a simple scalar field. But it's one that people have developed techniques for, and there are calculations. I'm not going to go into those details because I was told that you'll learn more about entanglement entropy later in the course. But I will say that if I assign this problem to you, I know what the answer is right away, namely it's divergent or it's infinite. And it's the result of a UV divergence, namely that the answers or the field theory is actually degrees of freedom are correlated very strongly at short distances. And so it's this calculation is going to be dominated by the short distance correlations in the vicinity of this blue curve that I call the entangling surface, the surface that divides the inside and the outside. And so to make sense of this problem, we really have to regulate the calculation. We're going to have to either introduce a buffer physically in our calculation, or we're going to throw away short distance wavelengths. And then what you'll find is the answer takes a form like this. It's going to be a ratio of some macroscopic scale characterizing the size of the system over the short distance cutoff scale to various powers, where d is my space-time dimension. So if I think about d equals 4, namely we live in 4 dimensions, three space plus 1 time, then this would start with an r squared over delta squared. The second term, it looks like it's a constant, but there's actually a technical detail that in 4 dimensions, I get a log term here. I get the log of r over delta. In any event, to make progress, what we would do is actually do not just the calculation for this particular configuration, but what you might try and do is do that same calculation, but for many different entangling surfaces. I divide up my time slice in many different ways. And if I assess the different answers, what I would see is there's a similar structure, but that I could interpret this first term, this term that I said started with r squared over delta squared, as in fact the area of the entangling surface over the cutoff to the appropriate power times some coefficient here. And the subleading terms actually have an interesting geometric interpretation as well. You can think of these or the next term as being the integral of some curvature or some combination of curvatures, some geometric factors over that surface, and so on to higher powers if I'm in some large space-time dimension, or I'm imagining a calculation in some large space-time dimension. But the thing I want to focus on is I have an entropy here, and it's proportional to the area of some surface. Now, in thermodynamics, where we probably first learned about entropy, we were taught that entropy is an extensive property of a system, and it grows like the volume. But here I've got an area, so the question is, where have we seen that before? And, well, hopefully we've seen it before in discussions of black holes. And in fact, this is really the root of the collision that I talked about on my first few slides, because it goes back to 1973 when this gentleman, Jacob Bekenstein, was just a graduate student in Princeton. But he wrote a paper called Black Holes and Entropy, where what he said is, I want to think about black hole physics from the point of view of information theory. And he concluded through various thought experiments that consistency demanded that black hole horizons, have an entropy that's proportional to the area of the horizon. And this is only part of the story, because that was followed in the following year by work by Stephen Hawking, where he showed that in fact, when we think about quantum fluctuations, black holes aren't black, but in fact they leak, emitting black body radiation with a temperature, the Hawking temperature, which again is proportional to various fundamental constants times the surface area, or a canonical acceleration that characterizes the black hole. Now, if we go back to the entropy formula up here, it's quite a remarkable formula in that it combines all sorts of different aspects of physics. It becomes a watering hole for lots of different ideas, where we bring together lots of different ideas. We've got the area, which is geometry. We've got c, the speed of light, from special relativity. We've got Boltzmann's constant from thermodynamics. We've got an h bar from quantum theory, and we've got Newton's constant from gravity. And in fact, seeing quantum or h bar and g next to one another, or quantum and gravity, many people have thought, and it was long, thought that this is a window on quantum gravity, and whatever our theory of quantum gravity is, to be consistent, it has to be able to reproduce this Bekenstein-Hawking formula for black hole entropy. Now, if we step back, though, from a modern perspective, there's something really remarkable going on. I mentioned thermodynamics, but often, we think of entropy from the perspective of statistical mechanics. And in that case, it's telling us something about the microstates that make up some big system. And so here we have some information about the quantum gravity microstates of this black hole. And what we're being told is that that information is encoded in the space-time geometry through the horizon area of the black hole. Which is just, when you think about it, it's just a truly remarkable observation or result. I've also rewritten this formula. I've absorbed all of those constants, and what we find is that quantum gravity actually provides us with a fundamental scale, the Planck scale, which, again, I'm a string theorist, so I work in some arbitrary number of space-time dimensions. And so what appears here is the Planck scale to some power, the space-time dimension -2, and it's given by the combination of these fundamental constants. And that really plays a key role in understanding quantum gravity. This is an unbelievably, compared to modern physical experiments, an unbelievably small scale. But when I said we're observing space-time at short distances, I really mean that we're observing space-time at these distance scales. The key idea, or the reason I introduced this idea, though, is because here we have an entropy, and on the other side of the equation, we see not a volume, but instead an area. Now, this at the time was seen as a peculiarity, but back in 1984, a researcher here at Perimeter, Raphael Sorkin, he really started thinking about entropy and entanglement entropy. He actually invented this concept without using the words. I mean, entanglement entropy entanglement and entropy were not two words that came together. But what Raphael realized is that the calculation I described, the calculation of entanglement entropy in quantum field theory, gave a result that was proportional to the area. And so he found that that was very suggestive that if this cutoff was in fact the same, the short distance cutoff delta over here that we had to introduce to make sense of the quantum field theory calculation, was of the order of this Planck scale, the scale at which quantum fluctuations become manifest in our gravity theory, then in fact these two theories could be lined up, where the horizon, which divides the inside of the black hole from the outside of the black hole, is a natural surface for which to calculate the entanglement entropy and to get a result, well, this famous result then. And this was, well, elucidated in, a paper with co-authors, but then in fact, it sat fallow or ignored for many, many years. And about a decade later, various scientists who were interested in this question rediscovered the idea and brought it again to the fore of high energy physics research. So again, here's my collision slide, and I'll pause and ask if there are any questions at this point in the lecture.
You can also leave the questions in the chat and I can read it without problem.
Okay, and no questions. is fine. It also gives me an excuse to take a drink and moisten my throat. So I'll just carry on. But again, feel free to ask questions whenever they arise. And perhaps the best way is to put them in the chat, and that way Daniel will notice them. And he can point them out to me.
Sure.
In any event, we talked about an idea, entanglement entropy from quantum information. We talked a little bit about quantum gravity, and we said that holography is a common ground between these two. So how are we going to combine holography and entanglement entropy? And again, my understanding is you're going to talk more about this in the course, and so this is going to be a very quick introduction. But this goes back to work, almost 10 years ago or 20 years ago now. Wow. By our friends Shinsei Ryu and Tadashi Takiyanagi. And what they realized is in the context of holography, we have this boundary quantum field theory. There's no gravity here. And so, if I think of this as a time slice in the boundary space-time, I can ask the question, what is the entanglement entropy for some region in my boundary space or time slice of my boundary space in this quantum field theory? Now, I said that it was a difficult calculation to do for even a simple scalar field. Now we're talking about a conformal field theory, which is strongly coupled and has a large N theory with a huge number of degrees of freedom. And so one can imagine that this, as a quantum field theory question, is, extremely challenging, if not nearly impossible to carry out within that context of conformal field theory. On the other hand, ADS-CFT gives us a dictionary and gives us the opportunity to translate this difficult question in the boundary quantum field theory into a geometric question in the bulk. And it's not obvious how to do this, but what these folks proposed is the following formula, that I should consider all surfaces in the bulk that are, this little symbol means the surfaces V are homologous to A. Basically, that means if that surface was shrink wrap, it could be pushed back and fill the surface A in the boundary, or the region A in the boundary. And on all of those surfaces, what I'm supposed to do is I'm supposed to evaluate the Bekenstein-Hawking formula. That's a formula that we realize is associated with an entropy, but it's a black hole entropy. And I'm supposed to extremize, all of these values of the Bekenstein-Hawking entropy over all possible surfaces. And the extremal value extremizing picks out a very special surface. And it also gives me a very special value for this formula. And that's the quantity that I associate with the entanglement entropy for this question that we posed in the boundary theory. Now, as my little picture here indicates, at the time that this was proposed, this was like pulling a rabbit out of a magician's hat, and many people, including myself, didn't know what to do with it. And in fact, I actively ignored this result for at least 4 years afterwards. And the problem was that, again, before even making the first steps in the calculation, I know what the answer is. The answer is infinity. But, if we understand the quantum field theory calculation, we know that that's exactly the right answer. It should be infinite. Here it's infinite because I'm integrating over surfaces here. In my cartoon, this is an integral this is a surface that extends all the way out to r equals infinity, or the boundary, so-called boundary of my ADS space. And so it's natural that there's an infinite amount of area there. And so the answer is going to diverge. But this exactly corresponds to the kind of divergence that we saw in the quantum field theory. And in fact, in ADS-CFT, you may have heard that, the higher the energy of the degrees of freedom in the boundary theory, they're sort of associated with larger and larger radii in the bulk. And so it's natural to think that a divergence that's associated with going to R equals infinity is in fact a UV divergence in the boundary theory. And usually what we do in calculations like this one, or any simple calculation, including correlators or scattering amplitudes, is we introduce a cutoff surface. We don't integrate out all the way to infinity. We integrate out to some large radius. And in fact, there's a prescription, or part of the dictionary tells us how the short distance cutoff in the boundary theory is associated with this large radius in the bulk. And in fact, the ADS scale, or the curvature scale of my ADS geometry, provides the appropriate conversion constant. In any event, if we do that, what we'll find is that now we get a finite answer. And if we look at the leading contribution, you'll get a bunch of factors here: the ADS scale to an appropriate power, Newton's constant, and then we'll get the area of this surface measured in the boundary theory over this cutoff to the appropriate power. And so that's precisely has the form of the area law that we saw, or that I said would arise in a field theory calculation. But let's look and see a little bit more detail how it arises here. You might recall that this is at least one metric on an ADS geometry. This is often called the Poincare coordinates, although you may think of it in where there's a coordinate z, which is actually the inverse of this r. But there's a flat bit here indicating the gauge theory directions. There's a factor here saying that this part of the metric grows very, very large as I go to r equals infinity, and then there's the radial part of the metric here. Now, if this is our region in the time slice at infinity, I'll introduce a coordinate that's orthogonal to the surface. I'll adapt the coordinate so there's a coordinate that's orthogonal to all of the directions on the surface, and I'll introduce some coordinates that run along the surface. If I look at my picture of the ADS, here's the boundary, here's the bulk down here, and it turns out that all of the surfaces, no matter what they are, to leading order, what they do is they fall straight down into the geometry. And so the leading part of the answer is relatively easy to calculate. One is, in fact, then just integrating the induced metric on this surface as a function of the appropriate coordinates here on the I need coordinates on the world volume here of my extremal surface. So I'll choose these coordinates that run along the boundary directions, and I'll choose the radius into the bulk here. And so then this evaluation turns into something like this, where I put together the y contribution, which picks up various factors from the metric, and then there's the radial contribution. And I don't really have to worry about bending anymore, or for this particular evaluation, again, because the surface falls straight into the bulk. But if you put all that together, you get the area measured in the boundary metric over 4g from the Bekenstein-Hawking formula, and then there's this radial integral, and what we're considering is the dominant contribution coming from large radius, or from the cutoff surface. You put all that together and you get an answer then that looks like this, where we've introduced, again, a more precise formula for a factor of the ADS curvature, over G Newton, and then this area of the boundary surface or the entangling surface over the cutoff that we introduced here in the boundary theory. And I can actually carry that calculation out to larger orders, higher and higher orders. It turns out that these coefficients are cutoff dependent, and so they're less interesting. But if you go to high enough order, you find that there's this logarithmic contribution, which is not sensitive to the cutoff. And so this coefficient at that order, d minus 2, is actually a universal contribution. And that has all sorts of implications, or there are fun things you can do with that, but I'm just going to pass over that at this point in time. What I am going to talk about, though, again, this was a conjecture, and what happened is people studied the conjecture, and basically what we were doing was we were learning more and more about entanglement entropy, and every time we learned a new lesson from entanglement entropy or quantum information theory, we checked to see, does the Ryu-Takayanagi prescription give us that same answer? And so I wanted to describe some of those. I said that these calculations were extremely challenging. Well, it turns out in a two-dimensional CFT, we have a lot more symmetries, we have a lot more control of the theory. And so these two authors, Pascal Calabrese and John Carty, did calculations that applied for any two-dimensional CFT. In that case, we're talking about my time slice is just a line, and the region is then just a line segment. To make it more interesting, I might, instead of having an infinite line, I might put my theory on a circle. And then as illustrated here, I'm considering an interval. My region A is this interval of length L, which is a small part of the full circumference of my time slice. And they went through a calculation and came up with an interesting formula like this. There's the central charge of the CFT, and then this particular formula that involves the circumference, the length, and the cutoff. Now, this is a result that has to apply for any CFT, and so it had better apply for holographic CFTs. And if you apply the Ryu-Takayanagi prescription in a three-dimensional ADS space, you find that you hit this formula right on the nose. And so that's a confirmation that their formula or their prescription was working. And there's a similar prescription for the case of a thermal ensemble. In that case, the circumference is replaced by the temperature and the sign turns into a sinh, but it's very, very similar. You can do a bulk calculation, and in that context, what you're doing, if this is a cartoon where this is the boundary of my ADS, I'm introducing a black hole in the bulk theory now, rather than just thinking about empty ADS. And this is, well, something you'll either learn about, or it's something that you already know about, that, you know, if I want to talk about a thermal bath in the boundary theory, I'm talking about black hole spacetimes in the bulk. And again, you do the Ryu-Takayanagi calculation for a three-dimensional ADS black hole, and you hit this formula right on the nose. So again, it's an indication that things are working well. A couple of other simple properties of entanglement entropy. If I have a pure state, so that the inside and the outside complement one another, it turns out that the entropy is measuring the same set of correlations, and so the entanglement entropy for the inside and the outside is identical. In the holographic setup, that's simply realized because there's one extremal surface. It only cares where the endpoints or the entangling surface is in the boundary. And so you're naturally going to get the same value for these two entropies. On the other hand, again, moving towards thermal ensembles, this is a mixed state, and so these two entropies don't have to be equal. In fact, they shouldn't be equal. And you can do similar calculations or make similar arguments for black hole spacetimes. In that case, generally, I expect to find two different surfaces, one that's homologous to A and the other one that's homologous to the complement or the outside region. And so again, you recover this simple property. There are a number of other properties, again, thinking about thermal baths. We know from thermodynamics that there's a thermal contribution, and that can be related to a contribution coming from the black hole horizon itself. There's an interesting formula called strong subjectivity, which actually, by very simple, manipulation of pictures, you can show that this inequality for overlapping regions is satisfied. This picture applies for a static geometry in the bulk. It was extended to more dynamical settings by Aaron Wall, and it gave rise to other various inequalities, which are being studied in detail by many people now, including Veronica Hubney, who I believe might be one of the lecturers later on in the course. But we moved from just there are many more consistency tests that people studied, but we moved from, just having consistency tests to actually proving that this was the right formula in various contexts. With an Indocina, I proved it for a circular or a spherical entangling surface in general. Lukowitz and Maldacena then extended our work to have a more general proof, which again applied in static spacetimes. But then Zhidong, Eter Lukowitz, and Mukund Rangamani extended the proof to general spacetimes, so that this was no longer a conjecture, but in fact, it's proven. And as a result, holographic entanglement entropy really became a fruitful forum for a dialogue between the bulk and the boundary, by which I mean, by studying this entry in the holographic dictionary, we learned new lessons about quantum field theory, and at the same time, we learned new lessons about quantum gravity itself. And so emerging from all of that discussion came a slogan, which was that space-time geometry was equal to entanglement, namely that entanglement was a key property that had to be taken into account, or that the boundary degrees of freedom had to have a lot of entanglement for the space-time, the bulk space-time, to really emerge in the holographic discussion. And there are lots of different discussions or points that I might raise here. The most exciting being that recently holographic entanglement entropy was really a key to understanding the page curve, or the behavior of black holes as they emit Hawking radiation and evaporate away to nothing. And there's been there were two seminal studies in 2019, I believe, and that just resulted again in a watershed. I mean, it was a real milestone and produced all sorts of interesting results. I wanted to show you very briefly just one idea that emerged, and it has to do with a remarkable property of general relativity. Originally, space-time was thought of as a stage upon which physical phenomena take place, but when gravity is being considered, what Einstein theory shows is that space-time is not just a stage, but it's actually a physical agent. It's an active participant in the physics of gravitational dynamics. And so the reason I'm saying that is I'm just going to show you how, in fact, that arises in an entanglement discussion. Here I have to step away, actually take one baby step beyond entanglement entropy. Instead, we're going to talk about the relative entropy, which describes correlations between two different states. And so this formula here, I've got, well, up to the minus sign. This is just the standard entanglement entropy of this first state. This is a different formula. It has the same structure, but it combines both my state, or the density matrix describing my state, rho 1, and the state rho naught. And I'm going to think of rho naught as my reference state. I'm going to think that rho 1 is a slightly excited or a perturbed state. And what this is describing then is the extra correlations or the extra entanglement that's created by that perturbation or that excitation. Now, what our quantum information friends, or actually our friends from algebraic quantum field theory, have introduced is basically they think of a density matrix. It can be thought of in terms of what they call the modular Hamiltonian. Basically, what they're doing is they're just taking the logarithm of that object. I mean, it's actually it's far more technical, but you can think of it as basically what I'm doing is I'm taking the modular Hamiltonian here as being the logarithm of this density matrix. And if you manipulate these formulas and you think that the rho 1 is a small excitation above rho naught, what you'll find is that this formula yields a simple result, which is known as the first law of entanglement entropy, namely that the change in the entanglement entropy between rho naught, going from rho naught to rho 1, is equal to the change in the expectation value of this modular Hamiltonian. When I take that expectation value first in rho naught, and then I subtract that away from the expectation value in rho 1. And that set of words, I hope it sounds familiar in that that really is the first law of thermodynamics when I think of rho A, or my rho naught, as being a thermal state, where this exponential really is the true Hamiltonian of the system. There's an extra factor here, the temperature, which is hidden in my modular Hamiltonian. But if I apply this result to this simple density matrix that we're familiar with, we realize that this is just the first law of thermodynamics. This is the change in the entropy. And on this side, I get the change in the entropy divided by the temperature. Now, generally, the modular Hamiltonian is just a big mess. I have some density matrix. I'm trying to take the logarithm of that. In this case, that would be simple. It's just the Hamiltonian divided by the temperature. But generally, if I have a quantum field theory and I pick some state, or I pick some region, I pick a state, I just get some non-local, mess. And so we couldn't make much progress. On the other hand, there's one case, at least one case, where it has a simple form. And that's for a conformal field theory, which is relevant for holography. And it's for a spherical entangling surface. And what you can show is that the modular Hamiltonian is proportional to the energy density. And so it's starting to look like a Hamiltonian. But there's some geometric factor here that depends on the radius of my sphere. And we're integrating over the position inside the sphere. Now, given that relatively simple geometric result, for this again applies for any CFD, but you can ask, how is this realized, or how do we realize the first law of entanglement in a holographic setting and make use of this result? Well, we can take our ADS space and we can make some we can introduce some gravitational waves or excitations. That's what these wavy lines are supposed to indicate. This involves the stress tensor, and so that's something that we measure at the boundary of the ADS space, and so that's we can do a calculation to evaluate this expectation value. On the other hand, the entanglement entropy is related to an extremal surface. And so this part of the equation is related to, changes in this geometry deep in the bulk. And if I don't evaluate it simply for one surface, but I evaluate it, in fact, for all possible surfaces of all sizes, all positions, in all different reference frames, what you realize or what you find is that this puts a constraint on the excitations here that I can introduce in the bulk. Namely, consistency demands that the bulk geometry, or that those excitations are in fact gravitons, satisfying the linearized bulk Einstein equation. And so by taking this entanglement idea in the boundary theory, we start to see hints that our holographic theory is actually a dynamical theory of gravity. And so that's sort of an entanglement realization of this, where entanglement is not just telling us how to grow or how to measure the space-time. It's actually telling us that entanglement tells us about the gravitational dynamics. Now, I'm going to take a break in just a second. I can see that I'm running slow. But here's our my favorite slide, holographic entanglement entropy. We have our slogan. And so it was a little bit disconcerting when a few years later, Lenny Susskind came along with another slogan, and he said, entanglement is not enough. And what he meant was that entanglement entropy is not enough to do all of the interesting physics that we're interested in. This is one diagnostic of, or we can use that as one diagnostic to measure physics in the ADS CFT, but it's not going to give us a complete picture. In particular, what was he interested in? He was interested in the physics of black holes, and in particular, the physics behind black hole horizon. And here I have this beautiful picture of M87. No, actually, that's Sagittarius star from the EHT collaboration, or the Event Horizon Telescope. But the kind of pictures I'm going to show you today are these stick figures, or simple versions of black holes, or ADS black holes. And I'm not sure if we've introduced this yet in the course, but this is a Penrose diagram. And so basically, spatial directions run horizontally, time runs up. A key factor is that null rays, or null directions, run at 45 degrees. In the picture, I see that there's for an eternal black hole, there's a singularity in the future. That's the singularity that would form if this was a real black hole that arose from the collapse of a star. But in the maximal analytic extension, there's also this singularity in the past, or this white hole region. What's interesting is that there are also two sides of the black hole. There's two sides to the Einstein-Rosen bridge. And so there are actually two ADS boundaries here, these vertical lines. And that indicates that there are actually two CFTs that are needed to describe the physics of this geometry. And in fact, what Juan Maldacena argued is that it's described by what's called a thermophile double state in the boundary theory. And so they're actually, a combination, and entangled combination of energy eigenstates on the two sides of the CFTs on either side of the Einstein-Rosen bridge. And of course, if I integrate out one of those degrees of freedom, I just get a thermal density matrix for either the right or the left theory, and hence we get the physics of a thermal bath, or a thermal ensemble. Of course, I pointed out the singularity. That's where interesting new physics is going to happen. That's what Lenny was really chasing. And so this is the region of the diagram that he wants to study using these quantum information probes. But, there are simple arguments to say that entanglement entropy won't be able to tell us about the geometry there. And I'm just okay, I'm going to run through this very quickly. I see I've already gone past the hour, but if I think about the Einstein-Rosen bridge and I pick two, say, identical regions in both boundaries, I could ask, what is the entanglement? What is the minimal surface? And what I would find is what's shown here. If this is a picture of the Einstein-Rosen bridge, here are my two regions and the boundaries. And in fact, the entanglement or the RT surface would have two components that would join the endpoints of these two regions. And so these two RT surfaces would span the entire Einstein-Rosen bridge. If we push them, wrong way. If we push my regions up in the diagram, if I go to later times, I'd get a similar configuration, but now it would have to stretch through the interior. It wouldn't go through the bifurcation surface here. And so they would start to get stretched and the entanglement entropy would start to grow. And that would continue for a while, but in fact, after a sufficient time, the surfaces would break, or alternatively, the minimal area surfaces would be these two individual surfaces on either side of the black hole. And that's something that's really enforced by one of these inequalities called subadditivity. And it says that the entanglement entropy of the individual regions has to exceed the entanglement of the combined regions. And these surfaces that span the entire Einstein-Rosen bridge just grow and grow and grow. And so eventually you would violate these inequalities. And so they cannot be the minimal area surfaces. And here we're just continuing up. What Lenny realized is that entanglement, or what he argued is entanglement entropy, well, it's a very robust probe of the boundary theory or our mixed states. It's something that's only sensitive to the eigenvalues of the density matrix. And he would like a probe that's more sensitive to the details of the density matrix. And his proposal was holographic complexity. And so this is a time where I am going to change track again, but so I'll first ask if there are any questions, but then I think we all deserve let's say a 5-minute break. I see another question here about the thermophile double, which points out that this, let's see if we can find it. This thermophile double state is a purification, or what's called a purification of the thermal state or the thermal density matrix. That just means that if I have this mixed state, I introduce extra degrees of freedom and I produce a pure state where if I integrate out my extra degrees of freedom, I get the original mixed state back. And so this is an example. You can think of this, say, if I started with the thermal density matrix for the degrees of freedom on the right side, or this theory, this is a purification of that thermal density matrix. The intuition that I tried to give you about why it arises here is the simple idea, first of all, that there's one geometry here. We're not confused about what the geometry of the eternal black hole is. If there was something, you might think that if there was something falling into the black hole and once it falls past the horizon, or rather, if there was a star that collapsed and formed the black hole, we might not know what's fallen into the black hole, and so there might be some uncertainty. And so that might require a density matrix to describe that space-time. But in this case, we have, this very smooth, very regular space-time, apart from the distant future and past. And what I pointed out is that because of the Einstein-Rosen bridge, there are actually two different asymptotic boundaries. And in the same way that I associate conformal field degrees of freedom with this boundary, like I can measure correlation functions, I can measure expectation values on this side. I can do the same thing here. And so it's natural to think that each one of these boundaries, or associated with each one of these boundaries, is a separate set of degrees of freedom, each one of which corresponds to the same CFT now in some excited state that we associate with the usual ADF CFT. I'm not sure if I answered the question, but that's how I would explain it.
Okay, great.
Okay. Let's see if we can. I'm going to get rid of this. Okay. Okay, we took our break, part 2. Okay. So now we've moved into a new area, holographic complexity. Just as I started before, I had to explain a little bit about what entanglement entropy was. Now I'm going to explain or try and give you a caricature of what complexity is. It's something that's discussed in the context of quantum information theory, in the context of computer science, and it is what it sounds like. It is how difficult is it to implement a particular task. So you might imagine that computer scientists are interested in, how difficult is it going to be to decode a particular message or to crack the coding of the banking system or something like that. The question that we're going to be asking or referencing today in the holographic context is, how difficult is it to prepare a particular quantum state? And we're going to rely on something that the quantum information folks have created. It's called the quantum circuit model. And so I start here with a reference state. I'm going to think of that as some simple state, in particular an unentangled state, since I want this measure to be telling me about the entanglement of the final state. And so here I've illustrated it, if I have a series of spins, they might all just be spin down. That might be my simple reference state. And then what I'm going to do is I'm going to build a unitary that takes me from my reference state to whatever my favorite quantum state is, or my target state. And there's always going to be a unitary that takes me from one vector in the Hilbert space to another vector in the Hilbert space, or one state to another. But I'm going to build this unitary out of a simple set of gates which only act on a few qubits at a time. And so there's an illustration here of a so-called universal gate set. You'll notice that they don't include more than 3 qubits at a time. And so what I'm instructed to do is to build a quantum circuit. Namely, I put those universal or those gates together in a particular pattern to take, say, my reference state on this side to a certain output, or my target state on this side. Now, if we're actually doing this with discrete gates like the ones I showed on the previous slide, or I might also introduce a tolerance. And what that means is that, in general, these gates give me discrete jumps. And so it might be arbitrarily, or it might be extremely difficult to hit a particular target state. And so what I'm going to say is, if I get my state, my psi here, to be within epsilon by some measure of the target state, then I'm going to declare success, and I'm going to say my job is done. What is the complexity then? Well, I'm supposed to consider all possible circuits like this, and I find the most efficient one. And I count up the number of gates, the minimum number of gates, i.e. the number of gates in my most efficient circuit, and then I that number then gives me the complexity. Now, one question, this is a very quick discussion, but, I made a lot of choices. I said, I'm going to choose a simple reference state. I'm going to choose a set of gates here to build my unitary, and I'm going to choose a tolerant. And you might wonder, is the answer that I'm going to get for this complexity going to depend on all those different choices? And the answer is, as I've indicated here, yes. And so the computer scientists usually ask questions like, if my system grows, how does the complexity grow with that? Does it grow as a polynomial power of the system size, or is it exponential in the system size? And and irrespective of the details of the choices I make, those properties are robust. And so that's what the computer scientists have focused on. In holography, we're going beyond those particular questions. And so we're trying to, and it's part of the story, is to formulate physical questions that give us robust, or where complexity gives us a robust answer. And typically the way that we're doing that is we're not considering one particular transformation, namely we're going from our reference state to some one particular target state. Rather, what we're going to think about is that, we're going to do this problem many, many times, kind of like when I talked about the entanglement entropy. To understand it properly, we don't just do it for one particular entangling surface or one particular geometry. We do it for many, many different ones, and that gave us some insight, some new insight. Here, what we're going to do is we're going to have a single reference state, but we're going to compare the complexity for the choices that we make for many different target states. So we might consider thermal states with different temperatures or different, subregions, or we might evolve it in time for different amounts of time. And so all of those will give us different answers. And so we're going to try and extract interesting physics from that. Now, as well as postulating this idea that complexity is interesting, Lenny also made some proposals about what the holographic dual of complexity would be. And so there were two particular proposals that he put forward: complexity equals volume and complexity equals action. In the first case, and I'm illustrating it again with my eternal black hole, we're going to consider a time slice in the boundary. And so there's a time slice actually on both sides of the Einstein-Rosen bridge, or both asymptotic boundaries. And we're going to consider all surfaces connecting those two time slices. So we did this in holographic entanglement entropy, and the dimension, because the entangling surface was a D minus 2-dimensional surface, these were the Ryu-Takenagi surfaces were codimension 2. Here we're considering codimension 1 surfaces. So everything's bumped up in the number of dimensions by 1. What I'm supposed to do is I'm supposed to evaluate the area or the volume of those surfaces. I throw in a factor of G Newton, just like I did for holographic entanglement entropy. And in this case, I maximize the value of this volume, and then I take this combination and I assign that, or the proposal is that measures the complexity of the corresponding boundary state. For complexity equals action, I'm taking the same configuration in the bulk and the same boundary state, but what I'm doing is I'm considering a region here in the bulk. And what I do is I evaluate the gravitational action on this particular region. It's defined by light cones or light sheets shooting out from this particular surface, or you might think of it as the domain of dependence of this extremal surface that we arrived at here. And so this is a region of the space-time that's bounded by light sheets. And I evaluate the action. Again, the gravitational action. Again, the proposal is that yields a number which I can associate with the complexity of the boundary state. One of the interesting things of these constructions is that, I wanted to be able to probe at arbitrarily late times when I pushed these T left and T right up in the diagram. I still wanted my probe to be studying or being affected by the geometry or the physics behind the horizon. And that's certainly the case in these two, for these two proposals. Oh, there's the action. I'll also mention that some folks in Texas made another proposal that's also very simple. They said, take this Wheeler DeWitt patch and just measure the space-time volume rather than evaluating the action. That's a lot simpler. And it also yields a number that, as I'll describe, behaves in a very similar way and also seems like a viable proposal for holographic complexity. Now, I've described some interesting, geometric probes or gravitational quantities. And I've said that, we're going to associate that with the complexity of a boundary state. But you have to ask why. Why are these particular geometric probes special? Why are they telling me about complexity? And so there are actually two reasons. The first one being that if you study the time evolution, if I take the time rate, I take a time derivative of these quantities that I'm evaluating, and I think about it at late times, so just, one or two thermal times after, the Einstein-Rosen bridge, what I'll find is that basically the growth of both quantities is proportional to the mass. And why is that an interesting answer? Well, you can make a qualitative argument, or that's what Lenny Susskind and Adam Brown did. We're not thinking about any old quantum field theory. We're thinking about a holographic CFT. So again, that's a CFT or a quantum field theory with a large number of degrees of freedom. And we also know that the Hamiltonian or the spectrum of the theory, we think of it as being chaotic, i.e. there's a dense number of states and they're, randomly spaced. And so one can argue that based on these properties, for a very long time, the growth of the complexity should be linear in this particular configuration. What should the rate be? Well, it should be proportional to the number of degrees of freedom that are relevant. And so it was proposed that the relevant quantity measuring the degrees of freedom is the entropy, or the thermal entropy, the horizon entropy. But that's a dimensionless quantity, and this is a rate. We're talking about the time rate of change of the entropy, and so we need a quantity to make up the dimension. And so the proposal was that the temperature provides us with that dimensionful constant. And by choosing the temperature, say, rather than the size of the system, we have that the complexity is an extensive quantity. And so what we see is a graph like this that, basically the system, our black hole state is evolving. This is the thermal field double state, is evolving in time. And it's like I'm picking gates at random, and those gates don't make the state any simpler. They don't provide a cancellation, which we'll see in a moment. They just make the state more complicated, and so it rises linearly like this. We said that the rate was proportional to the entropy times the temperature. And in a CFT, it turns out that's precisely giving us the mass or the energy of the CFT state. And so that then is corresponding with the result that we found, or that I talked about previously, for these two observables. Now, I just want to point out this plateau up here. What I talked about, this linear growth, is what we're going to focus on today, but it's only part of a story. One expects that, what we're doing here is we're exploring a lot, or that the state, as it evolves, is exploring a larger and larger volume or part of the Hilbert space, but that eventually the complexity is going to saturate because basically we've, filled the entire Hilbert space and there's nowhere else to go. Then what happens is basically, or what's expected is the complexity just randomly fluctuates along. And at very late times, there may be what are called recurrences where the entropy drop or the complexity, the state becomes very simple, but then the complexity will grow again. Now, in the gravity calculations that I'm going to describe, I'm not going to see any of this. I'm only going to see this linear growth. On the other hand, I'll refer you to a very interesting paper from a couple of years ago by these folks. And what they showed in a simple two-dimensional model in JT gravity was that they could see this plateau once they took into account non-perturbative effects, i.e. summing over all possible geometries. And so that's a highly recommended paper, but it's not the subject of today's lecture.
Can I make a question? Sorry.
Sure, go ahead.
So how about the Poincare recurrences that you showed? Because their paper, I think that they cannot really get that, but do you expect some way to recover it?
Yeah, I don't know what technology one would have to do to really study the long time or extremely long time behavior at that scale. Yeah, I don't have an insight there.
Okay, thanks.
I mean, I do think, yeah, you need to have some extra understanding of what JT gravity is beyond this sum over topologies. But I mean, it's a very interesting question. So we got a check mark here. The other one is the switchback effect. Here, what I'm going to do is I'm going to think again about my thermal field double state, but I'm going to perturb it. But I'm going to perturb it in a particular way. Usually we think, at T1, we might introduce an operator or an excitation. We wait a little bit of time, then we do another one at T2 and another at T3, et cetera, et cetera. But instead here, what we're going to do is we're going to do perturbations in what are called a zigzag order. So these times are going to be arranged such that if T1 is early, T2 comes later, but then T3 is before T2. Then I go later again, then earlier, then later, et cetera, et cetera. And so that's what's meant by the zigzag order. It's straightforward to, in this particular state, to understand what that means. All I'm doing is introducing some Hamiltonian or time evolution operators like that. It's taking me between these different times, and I can go back and forth in the time. It turns out that the answer takes, or is expected to take, a special form. These are very long extended intervals in these straight parts. And so over that time, we expect that the growth is linear. And so there's a part of the complexity that's going to be proportional to just the differences in these times. But every time we turn around, there's going to be a time delay by the so-called scrambling time. And let's just, to give you a flavor for why we believe that's true, let's focus on this time T3. And so this is a particular operator. And when I unpack it with all of the different time evolution operators, I get an expression like this. I'm unpacking this string of operators up here. Now, imagine what happens if I take that operator out. Well, I'm going to start, say, with some state here. I'm going to apply the operator e to the I h times T3. And so that means I've got my input state here. And I imagine that that's a discretized version of my state, or it's a string of qubits. I'm applying these local operators, which are just giving me time evolution of the qubits. And so here, what I'm doing by applying these local gates is I'm advancing the time evolution for a while. And then I arrive at time t equals 3. And then I'm supposed to, so I've evolved back here, and then I'm supposed to evolve forward again. And so I apply another bunch of gates to evolve me forward in time. But the key thing here is that the green and orange gates are actually inverses of one another. This is taking me backwards in time. This is taking me forwards in time. So if I act with one followed by the other, they just cancel out. Similarly, everybody in the first row here cancels with everybody in the second row. And the next row is the same, and the next row is the same. And so basically, all of these gates cancel out. And so what might have looked like a complicated state because I had all these gates was actually a very simple state because all of the gates canceled out. Now, let's introduce the perturbation at t equals 3 rather than just leaving it empty. So I'm putting my W back in, and I'm imagining that only acts on a few qubits. Here I'm actually only acting on 1 qubit. Now I can go through the same exercise. I see this gate cancels that gate, this one cancels that one. But in this case, that cancellation can't occur because there's this extra operator, WL, sitting in between them. And so what happens in this case is most of the first row cancels. Similarly, most of the second row cancels. And there's a smaller cancellation, at least in my picture. And so what's happening is the effect of this perturbation is spreading out across the entire system. And so that's why there's a time delay in the linear growth, and that's why this is called the scrambling time. It's referring to the information of this small perturbation spreading out or being scrambled throughout the entire state. Well, that's a story that I can tell about the quantum field theory or about gates and qubits, but how does that realized in the geometric fashion, the bulk space-time? Well, again, I'm starting with this thermofield double state, so that's an eternal black hole. I'm introducing perturbations. What that means is I'm introducing probes, or it turns out the simple probe that people use are shock waves. So we change the geometry. We send in an energetic wave from the boundary, and we can follow through the dictionary between bulk and boundary, and you get a whole series of different shock waves in your geometry. And if you evaluate complexity equals action or complexity equals volume, as I'm illustrating here, what you find is that there is a linear growth, but that there's a time delay that's associated with each one of the shock waves. And so you reproduce the scrambling time here in calculations like that. And so again, what you're doing is you're matching the expectation between the boundary theory and a calculation in the bulk theory. But I have to say that in both of these cases, I made a reasonable physical argument about what's happening in the boundary theory. And then I showed you how, or I argued people have done calculations, simpler calculations in the bulk, and shown that these expectations are real. The expectations of our reasonable argument are realized. Now, what am I going to do with these ideas? So that's an idea, or gives you a picture about, there are a few others about why people think these observables are associated with complexity in the boundary theory. What are other interesting properties beyond this linear growth? Well, one of them I'm going to take a particular look at, and then I'm going to park and I'm going to have another discussion. And that is that just like entanglement entropy in my cartoon here, my surface is going all the way out to infinity, or my region here extends all the way to the asymptotic boundary. And so, in fact, we should expect that the results here are only going to make sense. They're going to be UV divergences, and they're only going to make sense when I introduce a cutoff surface, as we did, or as I described for holographic entanglement entropy. And if you go through the calculations similar to what I showed you before for entanglement entropy, what one finds is that there is some combination of ADS curvature scales and the Newton's constant. There's an integral over the boundary time slice, and then there's a power of the cutoff. And then there are correction terms involving curvatures. As I hinted at before, this combination of curvature and Newton's constant, you can translate that into a particular coefficient, I'll call the central charge, that counts the number of degrees of freedom in our boundary theory. And then there's some numerical coefficient here. So I'm getting UV divergences that have a geometric form, just as they did for holographic entanglement entropy. And at leading order, it's basically a volume divided by the cutoff to the appropriate power. I can do the same for complexity equals action. It's a little bit different because now there are extra boundary terms that you introduce in the gravity action, and they give rise to this logarithm. Now that logarithm is a little bit annoying because it involves the ADS scale, and it involves a more or less arbitrary factor here that is introduced in the construction. Now, this is supposed to be an answer in the boundary theory, and so it should not involve the ADS scale just sitting there like that. Just as where it appeared here, it appeared in a certain combination of Newton's constant and the ADS curvature scale so that I could understand it in terms of a dimensionless quantity, namely the central charge of my boundary theory. So that's rather annoying, but in fact, I have an annoying scale here and a freedom here. And so maybe I can cancel the two. Namely, maybe what I should do is I should pick alpha, it's a dimensionless quantity, as given by the ADS scale divided by some new scale, L. That's going to get rid of my ADS scale, and so my result is going to be independent of that. But how am I going to choose L? And there are various choices you could make. You could make it proportional to the size of the system, but then my complexity has a volume, log volume term, and so it's super extensive. That seems unappealing. I could make it proportional to the cutoff, and in fact, then basically this term, this divergent term, would disappear. But on the other hand, those boundary terms, or this quantity, appears or affects infrared contributions to the complexity. And so I would see it in other places. I'd see the UV cutoff appear in what were supposed to be finite contributions. And lastly, I could just say that there's some reference scale. There's some new reference scale that complexity requires. That's a little bit unsatisfying, but maybe that's the case. When we originally discovered this result, we definitely thought it was a problem. We thought there might be an issue that you can't properly define complexity equals action, and perhaps, that simplified the story, and I should focus my attention on complexity equals volume. But I'm going to set that aside. I'm going to park that, and I'm going to address another question, namely, well, I talked about various qubit systems when I talked about complexity, but what do I really mean when I'm thinking about a quantum field theory? In general, or in particular, we're interested in a holographic conformal field theory. Again, large number of degrees of freedom, strong coupling. Well, that's a tough problem. And, well, okay, actually, this is, again, me telling myself that I should pause for questions. So I will pause and ask if there are any questions here. If not, I'll just charge ahead and I'll say, well, you know, we want to take these ideas and apply them to a quantum field theory. And when we first looked at this question, we said, well, you know, holographic CFT, that's hard. But let's think about a simple quantum field theory, namely a free scalar field theory in some number of space-time dimensions. And what I've written down is the Hamiltonian here. One of the things that we saw was that we expect the complexity is going to be UV divergent, and I can think that that's associated with entanglement at very short distance scales. And so we're going to have to introduce a regulator. Let's regulate our theory by putting it on a lattice. And then I get an expression like that, where delta is my lattice scale, my UV cutoff scale. But if I look at this, I've got momentum squared, phi squared. And so this is basically a complicated harmonic oscillator. And so I've gone from a scary holographic conformal field theory, and I've reduced myself to saying, let's study the complexity of states in a quantum mechanics problem, namely this regulated, or this simple regulated quantum field theory. You know, one of the questions I'm going to ask is we're supposed to introduce a reference state. So what reference state should we introduce? Well, I'm going to, or what we chose, this is work with Roe Jefferson, what we chose was a simple factorized Gaussian, namely there's an xi associated with each of the lattice sites, and I'm going to consider a wave functional that's just the product of a whole bunch of these Gaussians, and the dispersion of each of the Gaussians is identical. It's governed by this omega naught. And that's actually an idea that we borrowed from some earlier work in the condensed matter theory literature on a topic called tensor networks. But in any event, that simple state is going to be my reference state. And so I want to manipulate that reference state. And so I have to introduce some gates. What kind of gates am I going to introduce? Well, again, the natural operators, I'm doing quantum mechanics at each of the sites. And so I have my X's and my P's. And so some simple unitaries that we're used to are, say here, a translation operator where I have the exponential of one of the momentum. And I've got then a C number. And that C number actually has this reference X naught, but I've also introduced an infinitesimal parameter epsilon, because I want my gates to make very small changes on the state. And I'm happy to introduce lots and lots of these gates to actually make substantial or macroscopic changes. There's an analogous operator here where I introduce the operator X naught and a different scale P. And so what I'm doing here is I'm shifting the momentum by a similar C number. And so these are translation operators. The operators get more interesting if I put an X and a P in the exponential. And so essentially what I'm doing with that Pj is I'm shifting in the wave function, I'm shifting Xj by this quantity, by an epsilon of Xj. So one of the other coordinate, or the field values at one of the other lattice sites. Here, the I and the j are different, and so it's straightforward to see that I'm doing a shift like that. Alternatively, the I and j are the same, and so I've just normal ordered it, or I've written it in this particular symmetric way. And in this case, what you find is that in some sense, you're shifting X by itself. And so alternatively, you can think of that, what this operator does is it rescales the X at a particular site, or the X contribution at a particular site. Okay, those are some gates. Of course, we could make even more complicated gates by putting, you know, 2x's or 2p's or any number of x's and p's up in the exponential. But let's think about the target state. What are some simple target states? Well, we can think about the ground state of my quantum field theory. And that's the work that I originally did with Rho. Or we can also think of the thermal field double state, because that was the thing that we think about when we're talking about black holes. And a key thing or a special thing about both of these states is it turns out that they're Gaussian states. When I look at the wave functional, they're always quadratic in the various arguments, the x's. And so it turns out that these two gates are going to be sufficient to take this reference state to either one of these two target states. And so that's the work that we set about doing. How do we build circuits? Well, we just take our reference state, take our target state, and then we find linear combinations of the gates or the Qs that take me from one to the other. And so here's an example. I could take my Gaussian with two oscillators, an X1 and an X2. I apply this rescaling gate for X1, then I introduce this state or this gate that mixes X1 and X2, and then to finish off, I rescale the X2. And so by doing that systematically, you can get from here to here, and it's an interesting exercise. Then you'll find that, you know, if you count up the number of gates, if you count these exponents, or you add them up like this, you get an answer that looks something like that. And one of the things I might note here is that I'm allowing, and we'll see why in a moment, I'm allowing these alphas to be arbitrary numbers. I'm not imposing that they be an integer. And you might impose, and that would make the problem more difficult, but we'll see in a moment that in some sense, we're going to be thinking about gates where these alphas are just arbitrary powers. And in that particular case, you never run into this tolerance problem because you can make arbitrarily fine-grained steps and you're not overstepping your target state. And so we don't have to think about a tolerance the way I talked about in my introduction. Recall, though, that I'm not interested in any arbitrary circuit. I want to find the optimal or most efficient circuit to evaluate the complexity. And so that's where we face our real challenge. We have an infinite number of ways, in fact, even with just two sites or two harmonic oscillators, I have an infinite number of ways in which I could apply these particular gates and get from the reference state to the target state. So how do I find the optimal circuit? Well, I'm going to follow some ideas introduced by Mike Nielsen and his collaborators, and they were actually borrowing ideas from Hamiltonian control theory. But they were addressing this question, and you know, they realized that the circuits are producing paths in the space of states going from the reference to the target. And if we think about discrete gates, we'll make jumps like this along these, you know, discrete lines in my simple cartoon. But if we allow ourselves to take small steps, we get, you know, we might be able to optimize by taking, you know, more refined paths through the space of states. And by allowing, you know, for shorter and shorter steps or for arbitrary powers in which we're applying the gate, in fact, the path approaches a smooth, continuous trajectory. And what Mike realized is that, you know, working with something smooth was far easier than working with discrete gates. And so he set up a formalism to think about complexity in that way, a geometric picture. And so in the present context, what I would do is I would think of applying a unitary that's sort of an an exponential of our generators here, weighted by certain coefficients that move me along the continuous path. And the Y's are sort of telling me at a particular point on the path which gates are turned on and in what, relative weight we're giving them. You'll notice that up here I don't have an epsilon, but in my integral I've got this infinitesimal, the ds of the integral, and that really replaces the epsilon. And so you can think that, for any infinitesimal step, I'm making a very small change to my state. There's a P sitting here which says that to really make sense of this, I have to path order this exponential. Namely, I'm applying the gates, or I'm applying these contributions for small values of S before I'm applying them for larger values of S. And so that really gives us a time ordering or an S ordering on this particular trajectory. And in fact, what he pointed out is, rather than thinking about the full transformation, let's think about the how, what is the operator that takes us from our reference state to each different point along that trajectory. And so rather than extending the integral here to 1, we just extend it from 0 to S. And we're integrating now over some dummy variable, S tilde. In this particular case, I can think of these YIs, the on-off switches, as a velocity, because I can take this particular combination. I take the S derivative of this operator at the point S, and then I apply the inverse, and then I have to take some procedure to identify the different elements of Y, the different components telling me which different gates I'm applying. But it tells me about, it then plays the role of a velocity in my state space. And so this problem of optimizing this transformation, it has an analogy with determining the motion of a particle by minimizing some particular action. And so, the action that Mike and his collaborator, Nielsen and his collaborators focused on was this one where I'm, strictly counting or evaluating Y at each point along the path, and that's telling me how many gates I'm applying at each different path. And this leads to a geometric problem, but what I'm studying is a geodesic problem in what's called a Finsler geometry. But I could imagine that there are other cost functions, or that I might get an equally interesting answer by minimizing some other action. And so here's one that may be more familiar. I'm calling this a velocity, and so this looks like the geodesic length along my trajectory. And so the cost function gets a new name, and we recognize that now what I'm doing, studying I'm doing a familiar problem. I'm studying geodesics in a Riemannian geometry. I can make it even more interesting by introducing a metric, and effectively what I'm doing is I'm saying that different gates are going to be counted with different weights in my complexity, but that increases it makes the geometry that I'm studying even more simple. Turns out it'll be also interesting to get rid of the square root and consider cost functions that just take some power of my velocity or my on-off switch. So that's very much like looking at the Polyakov action for a string theory. And basically what I'm doing is I've got an unusual action, and I'm solving for a particular path that takes me from a starting point, the reference state, to an end point, the reference or the target state. And so then I'm not going, oh my goodness, I'm not going to bore you with all of the calculations. There's lots of interesting geometry, interesting geodesics. But what you find is that after a lot of hard work, the problem was actually very, very simple. I, describe the reference state as this factorized Gaussian, where each of the xi's sits in a Gaussian factor. When we talk about the reference state, usually or the target state being the ground state, usually what we do is we look at all of the normal modes of the lattice or the normal modes of the quantum field theory, the momentum modes, and then we get a Gaussian. I mean, usually we don't talk about it in wave functionals, but the equivalent is ground state is that there's a Gaussian again of the normal modes weighted by the frequencies of each of the modes. And to make it dimensionally correct, I have to introduce a UV cutoff for the lattice spacing that naturally appears. Now, the interesting thing is that, this is the natural way to think of the ground state or the target state. I could evolve, or I could rotate my basis. It turns out that in terms of these normal modes, it's just an orthogonal rotation, and so the reference state is, again, a simple diagonal or factorized Gaussian in terms of these normal modes. And, what are the omega k's? Well, there's for a periodic lattice, there's some formulas that we go through. The key point, though, is that I can think of my reference state in terms of the normal modes and the final state. Turns out that the most efficient thing then to do is that all you're doing is you're simply scaling each one of these individual normal modes from the reference frequency here to the appropriate frequency that we see in the ground state. And we're doing that independently. And it's a horrible, well, it's not a horribly, it's a really interesting but complicated problem when you work in the position basis. But at the end of the day, you look at your result and you realize that all you're doing is this transformation in terms of normal modes. So let's evaluate the complexity. Well, if I use this particular cost function, which was just the geodesic length, I get a simple expression like this. It involves a sum over the normal modes, and there's a log. There's the reference frequency, there's the normal mode frequency, and there's my cutoff that appear in there. What can I do with that? Well, one of the things I can notice is that this sum is going to be dominated by the UV modes, or the modes that in this particular expression where the k's are near n by 2, and then that's where the sign is near 1. And then these frequencies are all more or less proportional to 1 over delta, the lattice scale. And so as a crude thing, what I do is I just replace all the frequencies by 1 over delta, and then my complexity reduces to this simple expression. There's a total number of lattice sites to a particular power. Notice that it's a d-dimensional lattice. So it's, well, I'll just leave it at that. There are d of these factors. No, I lied. It's a d-dimensional theory, so there are d minus 1 of these factors, and then there's time. But each one of those terms is contributing a log of 1 over delta, the lattice spacing over my reference frequency. And so if I think of just this first factor, the number of lattice sites, what that's telling me, n to the d minus 1 is the volume of my lattice divided by the lattice scale for the appropriate power, except that I've got this annoying half, and so it's the square root of that combination. Why is that annoying? Well, when I talked about holographic complexity and the divergences there, it was actually proportional to the volume, not the square root of the volume. So what can we do? Well, we can think about other cost functions, and in particular, where's that square root coming from? Coming from this square root here in the cost function. And that's what led us to think about these kappa cost functions where there's no square root, or the equivalent of the Polyakov action. In that case, you know, this expression with that approximation reduces to something like this, where I've now got a volume over the cutoff to the appropriate scale, and then there's a log factor that appears as well. And I can compare that to the holographic complexity, and I can see that, in fact, even though this is a holographic, a strongly coupled CFT, and this is a simple scalar field, you know, the answers, at least for the leading contributions, are starting to look the same. One of the things, though, is I've got this log factor and I've got this annoying frequency that I haven't specified yet. And so I'd better think about choosing that. You know, there are different choices I can make. I can pick an IR scale, then I get this super extensive expression, which, you know, is something perhaps familiar from my discussion of the divergences in complexity equals action, at least when I choose kappa equals 1. I can also choose omega naught to be proportional to the cutoff. In that case, the log factors all disappear, and I'm just left with this term of the volume over delta. And again, that's similar to the expressions that I got for both of my candidates for holographic complexity. In this particular case, it doesn't really matter what kappa is, just going to contribute to this number out in front. And so I've got a number of different choices that I made here. But I compare to the discussion I had when I talked about complexity equals action. I also had a number of different choices that I could make. And so, in fact, what originally appeared to be a problem is actually a feature. What we realize is that in these theories of when I'm discussing the complexity, you know, the reference state is naturally going to introduce extra information or an extra parameter. And that's reflected in our holographic calculations as this ambiguity or this new scale, which isn't naturally fixed by the discussion. Now, there are other ways I could compare, other things I could think about. But I realize that I've run over 12 o'clock, and so I'm going to skip over that. And I'm just going to say that, you know, this is actually only one simple story that I've told. There have been a lot of people who have thought about, you know, how do you actually define the complexity in the boundary CFT? And what I'm proposing here is that we really need a better idea. You know, when one first is introduced to entanglement entropy in a quantum information text, you know, it's some formula involving the eigenvalues of the density matrix. But for entanglement entropy really to take hold in quantum field theory or in physics discussions, you know, Cardy and Calabrese introduced this replica trick where this turned into evaluating path integrals, perhaps over some strange new geometries. But it elevated the discussion to a discussion that naturally applied in a quantum field theory. You know, complexity is similar. We're supposed to, you know, the textbook definition says find an optimal circuit, count up the number of gates, that's the complexity. But, you know, is there a way to produce a new definition or an alternate description of complexity where, again, we're talking about path integrals or correlation functions, or perhaps path integrals with weird operators, weird geometries, that I'm producing a similar result? And I'll just briefly say that there have been a lot of ideas put forward in the literature. You know, one of the interesting ideas is to change the name of the game. And instead of coming from some simple reference state, I take a well-known state, a state that has a holographic dual, and I want to evolve to some later state that also has a holographic dual. And you can use, well, in many examples, you can just use conformal primaries or operators in the CFT to generate those evolutions and to generate the circuits or the gates. And that's changing the rules of the game, but it gives a very explicit dictionary between a boundary, what you're doing in the boundary CFT, and what you're evaluating in the bulk. And so then I didn't get to the end of the talk, but this is as good a place as any to stop. You know, there are lots of extra slides, and I assume that all my slides will go somewhere and you can take a look at those. But before we close then, I'll just ask once again if there are any questions about the part of the talk that I was able to give. I see you moving, so you're still awake.
Is there any question?
Okay, so for instance, I think that you at the end you were like comparing your proposal withdrawal with these other ways that you can implement it as volume of action or something like that. But then
Yeah.
you would like to actually see some time evolution or have the switchback effect, for instance. Can you actually recover that in some way?
Well, you can use that as a, you know, we looked at the UV divergent terms. You can try and make other comparisons. Here are two. You know, one is something called the complexity of formation, which is sort of comparing the complexity that you need to prepare two vacuum states versus taking my two SCFTs and or my two quantum field theories and preparing them in an entangled state, namely the thermofield double state. It turns out that all of the, you know, the holographic proposals and our free scalar field proposal, you know, the complexity or the complexity of formation is proportional to the entropy or the entanglement between the two CFTs in this state. And so that's a check. We get something that works. Unfortunately, when you look at the time evolution of the thermal field double, you know, there, one of the things I emphasized is it's proportional to the mass in the holographic case. What you find is that it's not in the scalar field case. And in that case, it's really because, you know, what we understand in the holographic case is we've got this complicated theory. And as the thermofield double state evolves, you know, the state becomes more complicated in that it's exploring, you know, different regions of this vast Hilbert space. On the other hand, what was special about the thermofield double state for my free scalar field, it was a Gaussian. It was very simple. It was simple to prepare. And the thing is that when it evolves in time, it remains Gaussian. And so it's really, you know, stuck on some simple submanifold of the full Hilbert space. And so you don't really see, well, that's why you know, with hindsight, we don't expect these two to match up. But, you know, I think that's what you were pointing at. And in fact, you need a more complicated or more complicated field theory or a more complicated state to see something interesting like that.
And have you tried to generalize it for interacting theories?
I personally, well, we've made some attempts, but nothing that rose to the level of a publication. There was a paper by Anindya Sinha and I believe some of his students where he looked at a very special interacting theory. And, you know, of course, what they did is they come up with a really clever trick to simplify the interacting theory or the, you know, the interacting state to a quadratic problem that they could easily solve again. But I did think, well, it is a very clever trick, and I did think, well, this is an interesting step towards doing more general interacting theories, but I've forgotten the specific reference, but if you send me an email, I can look it up
Okay,
for you.
thanks.